Okay, folks, let's continue with our series of lectures on training. This is the fourth in the series. And today we are going to primarily discuss incremental update algorithms. So a quick recap of what we've covered so far. Please mute yourself, folks. We've seen that neural networks are universal approximators. We must train them to approximate any function. Networks are trained to minimize a total error or a loss on a training set, and we do so through empirical risk minimization. We use variants of gradient descent to do so, and gradients are computed using backpropagation. We also saw that vanilla gradient descent can be too slow or unstable. Better convergence can be obtained through second-order methods that normalize the variation across dimensions. Adaptive and decaying learning rates can improve convergence. We saw that. Methods like RMSProp that decouple the dimensions can also improve convergence. Momentum methods which emphasize directions of steady improvement and de-emphasize unstable directions also improve convergence. So let's move on. Here are the topics we will cover in the remaining 2 lectures of the series on training. Today we'll discuss incremental updates, and we will revisit trend algorithms in this context. In the next class, we will discuss generalization and various tricks of the trade for better training models. Our first topic is incremental updates. Now just so I have an issue here. Let me PPT for some of the demos. We'll get to that later. Okay. So our first topic is going to be incremental updates. Now, recall our training formulation. We want to train our network to approximate a function. For example, the one illustrated by this blue dotted line here. This means we want to learn the network parameters such that for any input x, the output will be as close as possible to the target function shown by the dotted line. Except we don't know the entire function that we're trying to learn. We only know the input-output relation at a small number of training points. And so over here, each of these lines shows one of these training points, including the input value and the corresponding output. And so we train the network to compute the correct output at each of these locations. And we hope that when it does so, it will actually learn a function that also gives you the correct values at these other locations where we don't have training data. And to learn this input-output relationship, we use gradient descent. And the way we do it, we initialize our network, which gives us an initial function, like this red dotted line. And then the gradient descent update adjusts the network parameters to reduce the average error over all of the training points, over which we compute our loss. So it will simultaneously try to minimize the error everywhere here, and here. And to do so, it is going to try to, because it's trying to minimize the error over all of the training points, it's going to try to push up the function over here, because over here the function is below the target function. It's going to try to push up the function over here. It's going to try to push down. What's going on here, guys? Turn off your mic. Okay. So it's going to try to push down the function here. The dotted line is the network output, right? And it's going to try to push up the function here. It's going to simultaneously try to do all of these to make this closer to the target function. And it's going to update the parameters to do this, and the updated parameters will give us a new function, like the one shown by this red curve, which may still be off. So in the next iteration of gradient descent, we will once again try to correct the error at all of these training locations. Again, we're going to try to push this up here. We're going to try to push this up here. We're going to try to push this down, this up. And we'll update our parameters to do all of this because we are considering all of our training points together, right? And we'll keep iterating this process at each time, and each time trying to correct the error at every training point. And until we get as close as possible to our target function. So this process, where we consider the total error over all of the training instances and update parameters to try to minimize this total error, is what we call batch update. You update the parameters after considering the total error over the entire batch of training data. The problem with this approach is that we simultaneously try to adjust the function at all of the training points. Now, in order to do this, and we can have millions or even billions of training points. And so, guys, please mute yourselves, right? And so, you're right, Gladys, I should do that next time. So in order to do so, I have to, for each update, I have to consider all of the training points before I make a single update to the network. And this can be an extremely high computational load. And so before I continue, we have a poll over here. Let me release the first poll.
Do that.
Mute yourself, guys.
快点啊！你又被蚊子咬了。
Folks, mute yourself. Okay. Ten seconds. All right. Let me end the polling. So again, all of these options are right. The actual loss function we try to minimize requires batch updates because the loss function is the average over all of the training data. And so the batch updates minimize the total loss over the entire training data. That's what they do. And so batch updates actually optimize the actual loss function because the loss function, remember, is the average divergence over the entire training data. But then this means that batch updates require processing the entire training data before we perform a single update. So that is the problem with batch updates. Any questions? Questions here? Anyone? No? Okay. So here's an alternative approach. An alternative approach is to adjust the function using just one training point at a time. So to give you an idea of how this happens, imagine you're trying to shape a handkerchief or some sheet into some shape. Then you could just sort of sprout hundreds of fingers and try to grab it at various locations and begin adjusting it at all points all at once. And that would be in some sense the optimal thing to do. But then we can also do it by adjusting the shape of the object of your handkerchief one point at a time, right? If you were to be shaping something, the way you do it, you'd pull a little bit up here, then you pull it up a little bit up there, press it at another place. You make small adjustments at one point at a time And if you do it carefully enough and slowly enough, eventually you're still going to get your handkerchief or your putty to form the shape that you want it to. And so that's what we are going to do over here as well. Instead of trying to adjust the function at all training points at once, we will consider one training point at a time and adjust the network parameters to reduce the error at that one point. So we might first select, for instance, this instance highlighted in yellow, find the function is too low, and adjust it by pushing it up a bit over here. Then pick up another training instance and adjust the parameters to reduce the error over there. And then pick up the next training instance and then adjust the parameters to reduce the error over here. And then select the next one and adjust the parameters to reduce the error over here. And at each point, we're going to keep the adjustments small. And eventually, when we have processed all the training points, we would have adjusted the function at every one of the training points and got an overall adjustment. Also, now, instead of making a single update after processing all the training points, we would have made an adjustment update after each training point. So in one pass through the data, if you have T training instances, you will actually make T updates as opposed to just a single update, after processing the entire training data. And so, because you're making T updates, the overall effect can be greater than you would get. Because you're making so many more updates, the overall effect can actually be greater than what you would get with a batch update. Now, this approach, where we update the function after each training instance, is what we will call incremental updates. Unlike batch updates, where we process the entire training data before updating the parameters, here we update them after processing each training instance. Wait, is that a problem? Can you hear me, guys?
I can hear you.
Yeah, okay. So, all right, so Tushar, to answer your question, if I have 1 billion training points, if I were doing batch updates, I would have to process all billion training instances for a single update. Whereas in one pass through this data using this incremental method, you're going to make 1 billion updates. And that is going to have making 1 billion updates, as we will see, can end up being a lot more effective than just, in any case, it's going to be more efficient, time efficient, right?
Oh, I was thinking about small batches actually. Like I was not thinking about the entire batch.
The batch is the whole thing,
Okay.
right? It's your entire training data.
Oh, okay.
Right. When I'm speaking of batch updates is the actual loss that you want to minimize. The actual loss you want to minimize is the average divergence over the entire training data, right? You want to, which is a proxy for the total risk.
Right, yeah.
And so that is batch update, right? This is an incremental update, where you're just making, updating things one instance at a time. And so here is the pseudocode for incremental updates. Within each iteration, we loop through all the training instances. Then as soon as we encounter process any training instance, we immediately update the parameters. Also, we will generally make multiple passes over the training data. So here, within each pass within the training data, you're going to make an update after each training instance, but then you will also make multiple passes over the training data. And so we call this the training pass over the entire training data an epoch. Within each epoch, if we have a total of T training samples, we will make T updates to the parameters that's within each epoch. And so one epoch and this incremental update is like a single update using batch updates. So now in the pseudocode for the incremental updates, this outer loop goes over the entire data. These are epochs. The yellow box shows the code for one epoch. We loop over all training instances. And for each training instance, we make an update. And of course, we keep making passes over the entire training data until the loss is converged. So you really do not want to do batch updates because your training data are generally so large that having to process all of the data just to make one update is highly, highly, highly inefficient. But hold yourself in peace. You can repeat all of these questions when I'm done with the incremental update portion of this lecture. So what is the problem with just doing something naively in the manner that I just explained? Simply looping through the training samples in the same order every time will not work too well. We can end up getting cyclic behavior. For example, if we had training samples distributed like this, 4 samples out here, 4 samples out here, and your function was restricted to be the shape of this curve, and we are trying to approximate the blue dotted line, then if we go through the data in sequential order left to right, when we process the instances to the left, the function will get down here to reduce the error on these points. But then this will end up rising on the other side. Then when you're done with these data points and you move over to the right, it's going to adjust the function here, push it down, but then it will push the function back up on the left-hand side. And so if we continue looping through the data in the same order, the behavior will repeat. When we update the data, update the model for the data on the left, the right side will go up. And when you update it with the data on the right, the left side will go up, and we'll get this cyclic behavior. So to prevent this, we must go through the data in a random order to get more convergent behavior. And here's what we would do. We'd pick our training instances randomly. We'd randomly pick one training instance and adjust the function for it, which would make the function go maybe up there a little bit. Then randomly pick another point. And maybe adjust the function out here, which would make the model go down here and change the curve like so. So long as you keep bouncing around and randomly selecting the points on each side, we won't get cyclic behavior and the function will get updated properly. So when we perform incremental updates, it's kind of important to go through the data points in random order, changing the order from epoch to epoch. And when we do this with random selection of training instances, we will call this method stochastic gradient descent. It's stochastic because we randomly select the training instances, and gradient descent because we adjust the parameters with the gradient of the divergence for that instance. So here is the entire pseudocode for stochastic gradient descent. It's the same as the pseudocode we saw earlier for incremental updates, but with one key difference. At the start of each epoch, we randomly shuffle the training data. This ensures that the training data are presented in a different random order each time you loop over it. Now, in principle, this is the same as randomly sampling our training instances without replacement for each update. So this is a stochastic update method, specifically stochastic gradient descent. And so the story so far, then any gradient descent optimization problem presenting training instances incrementally can be more effective than presenting them all at once, provided training instances are presented in random order. So this is stochastic gradient descent. Now this is for any gradient descent optimization problem, not just for neural networks. And as a general principle, it also holds for neural networks. Questions? Any questions?
Is it the same thing, like the same as a optimizer SGD?
Yeah, it's the same thing, right? This is the principle is generic.
Yeah. So when we prepare the data set, we data loader, we choose the shuffle to be true. So
Yes.
is it the same thing
That's
combined
exactly
with
it.
SGD optimizer?
That's when you choose shuffle to be true, you're basically doing what is in this yellow block. If you don't do it, then you're likely to get cyclic behavior and suboptimal estimates.
Okay.
Yeah. Anything else?
Can we say that one epoch means one update?
No, one epoch is one pass through the entire training data, right?
Oh.
So this is an epoch. This is an update. So an epoch is going to have T updates.
Okay, I see. Thanks.
Right? All right, so let me continue. So why does this process of incremental updates work and under what conditions? For the why, let's first consider a popular simplistic explanation. Let's look at an extreme example. Now, the loss that we compute is the average divergence over all of the training instances. Each training instance has its own divergence. The loss surface is the average of the loss surfaces for all of the training instances. So the gradient that we compute, the derivative that we compute, is also the average of the derivatives of the divergence for the individual training instances. So at any point, at any point in the parameter space, the gradient of the divergence for the individual training instances will point in many, many different directions. And the overall gradient is going to be the average of all of these guys, which will be perpendicular to the level set for the global divergence function. It averages the directions of the gradients for the individual training instances. But then now consider this extreme case where all of the training instances are identical. Now, the gradients for every one of the individual training instance will point in exactly the same direction. So the average gradient, how will it relate to the gradients for the individual training instances? Anyone?
It will be the same.
It will be the same, right? So if I compute the batch gradient, is the batch gradient going to be any different from the gradient I get from an individual instance? No, right? Because they're all identical. What this means is that I have spent time t to get the result that I would have got if I had just looked at one instance, right? So the gradients for every one of the individual training instances will point in exactly the same direction. And so the average gradient will be exactly the same as the gradient for any individual instance. And this means that batch gradient, which operates over all T training instance to get a single update, will just get you this one little update after having processed the entire training data. It's going to give you exactly the same update as what you'd have had if you had considered only one training instance. But with SGD, in a single pass through the training data, you would have got T updates and made a much bigger change. Now, you're not generally going to get data that are all identical, but even if the data are not identical but merely clumped together so that they are all very close to one another, the same situation still holds. SGD will give us a much bigger update than batch update for the same amount of computation. And as the data get increasingly diverse, the advantages of the incremental updates decrease somewhat, but they don't disappear. Now, questions? So you're unlikely to get exactly this kind of situation in most cases, right? You won't get yeah, having data of this kind is not going to be very useful for learning the function, but this was just meant to illustrate that, in the extreme cases, I was giving you an extreme case where it's very obvious that SGD is going to give you a better update than batch descent. And as you expand out towards more realistic data, that benefit still remains. But there are limitations. I mean, it's not that simple. So let's move on. The previous example provides some kind of a reasonable intuition, but it's not the complete story. So what are the conditions for when it will work and how well it will work? Now, typically, so here's the problem. Typically, when you learn these models, they almost never give you a perfect fit for every training instance. So what we will get is a function that has low average error over the entire training data. But for any individual training instance, it's always going to be wrong, like in this example. So here, I'm trying to fit a linear function to these data. And this line shows me the optimal linear fit for this entire collection of data. While this function has the lowest average error, for any individual instance, the error is not zero, right? If I were to use just one individual instance, I can always reduce the error. So if we performed SGD, each update would pick up one training instance, say this one, and then minimize the training error on it. And so SGD might move the line to something like this. Then the next update would pick some other training instance, maybe this guy, and then it's going to move the line somewhat like this. And so, and then the next instance maybe picks up this one, and then it moves the line to something like that. So as you keep operating on individual training instances, you're reducing the error for that instance, but end up increasing the error for other instances, and you're going to be chasing your tail. The estimate is going to keep on bouncing around, and it will be non-convergent. So to prevent this, we must shrink the learning rate with iterations. Eventually, the learning rate will get so small enough that the correction for the individual instances will not mess up the learned function. So here again is the pseudocode for the stochastic updates. The two key features here are highlighted. First, we must randomly permute all of the training instances within each epoch. Second, the learning rate is no longer fixed, but actually changes as we update the model. And ideally, it must shrink with iterations. But even if it is shrinking, it must satisfy some conditions to ensure that we have the possibility of finding the optimum. First, we have to ensure that no matter how bad your initial estimate is, you can get to the optimum. And so Robinson Monroe came up with this with these very nice criteria for root finding, actually way back in 1951. So now consider this. For any individual parameter, right, we are always updating the current estimate by some eta times dl over dw. Now suppose this derivative had an upper bound. And so let me say the upper bound was b. Just then over the entire sequence of training, so eta I is the ith estimate, right? Over the entire sequence of training, what is the maximum value by which I can update an initial estimate? That is going to be, even if I run infinite updates, the maximum value that by which I can update the estimate is going to be summation eta I b, where b is the upper bound on the derivative, which is the same as b times summation I eta I, right? So now this is the maximum by which I can update a parameter from its initial value. Now, how bad can the initial value be? So let's say in the parameter space, this is your optimal parameter. The initial value could be out here. It could be infinitely bad, right? So that means you want these updates to permit the initial value to travel from here all the way out here. So if that is the case, how large must this value be for this initial value to get all the way to the optimum? Anyone? How large must it be? Anybody want to take a guess? If your initial estimate is infinitely off, then this must be infinite, right? So that you can cover the entire gap from the beginning to the end. And so in the worst case, you want b times summation I eta I to be infinity. So b is an upper bound. So that gives us this criterion that the sum of the learning rates, the entire sequence of learning rates must be infinity. That is the only way you can ensure that regardless of where you start from, you can end up, you have the possibility of arriving at the optimal value. On the other hand, you also want these step sizes to converge, as you saw, because otherwise the thing is going to bounce around. So that criterion is given by the second term here. So the two criteria that you have is that you want your the step sizes, the learning rates, to be divergent series, meaning when you sum all of them, it must be infinity. On the other hand, they must be square summable. When you sum their squares, that must be finite. So did this make sense to you guys? Does anybody see why both of these criteria are required?
I'm not understanding the second criteria.
The second criterion was because, again, going back here, right? If your step sizes are always large, then the estimates are going to keep bouncing around. So you want the step sizes to keep shrinking. In the limit, you want the step sizes to go to 0, right? So that means, and this, if anything that satisfies this condition, there's a mathematical proof for this, that is going to satisfy that property, that as you keep that eventually the series, the individual terms are going to go to 0. And so their squares, the individual terms in this are going to go to 0. So they're square summable. At the same time, you want the sum to go to infinity. So that's going to give you this condition. Does that make sense?
Yeah, so it's just saying that the learning rate must be finite. Is it what it's saying?
So no, it says that the sum of the learning rates must be infinite. At the same time, the learning rates must shrink. Right?
Okay.
And so how do we quantify shrinking? If they are square summable, then it's guaranteed that they're shrinking. The learning rate is shrinking. So this one says they are shrinking. This one says you can go from anywhere to anywhere.
Okay. Thank you.
That makes sense? Yeah, Igli?
Did we choose squaring for any particular reason, or could we have chosen some other function of the step?
So you'll have to look at the Robbins and Monroe paper. It actually, there's a mathematical reason for it. You wanted this, and it's not very hard to derive. But basically, you want the norm of the series to be finite. So if you think of the entire series as a long vector in a vector space, that norm has to be finite.
Right, but the steps are always scalar, right? Why would?
So the sequence is the entire sequence is a vector, okay. Right? It's an infinite dimensional vector, right?
Okay, yeah.
Right, and the norm must be finite.
Right.
Okay. So now We want to get a learning rate that satisfies both properties. Can someone suggest something of this kind to me? 1 over x, right? Exactly. And just in case, here I have this on the slide. What is summation k equals 1 to infinity, 1 over k? What is this term?
Infinite.
That is infinite, right? But what is summation 1 over k squared? That's going to be finite, right? In fact, summation 1 over k raised to 1 plus epsilon is going to be finite for any epsilon greater than 0, right? So 1 over k is literally at the very limit which of sequences which satisfies square summability and divergence, right? And so this actually gives you a pretty good learning rate schedule. And more generally, we'll actually use other kinds of learning rate schedules, which may not be exactly this, but the learning rate schedules that you are dealing with, for example, in your homeworks, they all have this property that in the limit, they satisfy both these criteria. And you can see why these criteria are required. Any questions? No. Okay, very nice. So to see how SGD compares to batch updates, here's a simple illustrative example. The problem here is k-means, and the x-axis is the time taken to train, the y-axis is the training error, and the curves show how the error decreases with iterations. The red curve is for SGD, incremental updates. The green curve is for batch descent. Now, the vertical bar over here is an error bar. So in this case, the authors have run the experiments many times. Now, remember that when you run SGD multiple times, there's a random component to it. So you're not always going to pull up the same samples in the same order across runs, right? Also, your training data can vary from run to run. And so you will have a variance across runs. We will see where that comes from in a minute. And so this one here, this green, both these vertical bars show you the variance across runs. And you see two things over here. First, SGD converges in 10 seconds, whereas batch descent in the simple example, which had, I think, like 100 training instances, converged in 100 seconds. So there's an order of magnitude difference. At the same time, SGD converges to a much poorer solution, right? Much poorer error, 0.02 versus almost 0. So while SGD converges faster, there's a larger variance and the error is lower. And let's try to understand why this happens. But before that, let me show you the next poll. Anurag, can you pull up the next poll?
May I know, like, what is an online version mean?
Online is incremental.
Oh, okay.
I should have made it clear on this while I was talking about it. Okay, guys, I'm stopping this. It's a minute. Okay. All of these are correct, right? SGD is an online version of batch updates. SGD can have oscillatory behavior if you don't randomize the order of inputs. It can converge by faster than batch updates, but it can arrive at poorer optima. And SGD convergence to the global optimum can only be guaranteed if step sizes shrink across iterations, but sum to infinity in the limit. So we've seen all of these already in the lecture so far.
I have a doubt in question part B.
Yeah.
So even if we randomize the order of the inputs, I think still SGD should have oscillatory behavior because it is considering the gradient for a single data point.
That's what you fix by reducing the this term here. This second criterion is supposed to fix just that, right? Your step sizes keep decreasing. In the end, it's not going to oscillate.
Okay. Right. Yeah.
Right. So, okay. Now let's see why all of this. I try to understand this behavior. Recall that our network is actually trying to model a function. And ideally, the objective that we would minimize when we learn the network is the expected divergence between the function computed by the network and the actual function, except to compute this expected divergence, you need the real function, which we don't have. So instead, the loss we compute is the empirical risk, which is the average divergence between the actual and desired outputs computed at a sampling of training instances. And we estimate our parameters to minimize this loss. Now, we saw earlier that if I define my loss like this, if I take my expectation on both sides, this is simply going to be 1 over n summation expectation of the divergence of xi, right, for xi, which is going to be the expectation of the divergence of xi, divergence of x, which is exactly the expected divergence. So we saw that this empirical risk is an unbiased estimate of the expected divergence. Now, so the empirical risk is an unbiased estimator of the expected divergence, which is why we try to minimize the empirical risk, although there is no guarantee that minimizing it will minimize the expected divergence, right? Just because this is an unbiased estimate for this doesn't mean that minimizing this will minimize the second term. But then there's a second factor, which is that the actual empirical risk depends on the training samples that we drew. If we drew a different set of training samples, the risk for that you compute this thing depends on the specific set of training samples that you had. If you had chosen a different set of training samples, you'd have ended up with a completely different loss function, right? So how can we quantify this variation? Now I can write, if I can figure out how to pull up my, somewhere here is my whiteboard, let me see. Where is my Microsoft whiteboard? Come on, guys. So here, I have loss of W, right, equals 1 over n summation I divergence for xi. I'm just writing this in simple form. So if all of the xi's are independent, then I can write the variance of the loss is going to be the variance of 1 over n summation I divergence of xi, right? Which is going to be 1 over n squared, the variance of summation I divergence of xi. Now, if all of the xi's are independent, then in that case, what do you know about the sum of the variance of independent random variables?
It's variance of the sum.
It's the variance of the sum, right? So this is going to be n squared times summation I variance of divergence of xi, right? Which is going to be 1 over n squared times n times the variance of, let me write this. Come on. The variance of the divergence of x, right? And squared cancel. So this is going to be 1 over n, the variance of the divergence at x. So what does this term mean? This is the number of training instances, and this is the variance of the divergence between the output of the network and the desired output computed over the entire input space. And so we find that this is the variance of the loss. Now this term here tells you how much the loss will change if you keep changing your training instances. Each time if you have a different training data, you're going to get a different loss function. And so if you look at the loss functions over all of these different experiments with different training data, the variance in the loss function across all of those experiments is going to be this guy, and it's going to be inversely proportional to the size of the training data. And so the variance of the empirical risk is 1 over n, the variance of the divergence. Now, the larger this variance, the more the loss varies across experiments, and the greater the likelihood that the W that you estimate will differ significantly from the W that minimizes the expected divergence. Now, when you consider SGD, at each iteration, SGD focuses on the divergence of a single training instance, right? So if you take the expectation of the loss that is minimized at each iteration, that is simply going to be the expected value of this divergence, which is exactly, so the expected value of the loss that you minimize in each step in SGD is exactly the expected divergence. So this means that the sample divergence that we use, that we minimize with SGD, is an unbiased estimate for the expected divergence. But then the variance of the sample divergence is simply going to be variance of dive, right? So now if you compare this term with what we had when we had batch estimates, well, I didn't write it over here. When we had batch estimates, what was the variance we had if we had n training instances?
1 upon n.
1 over n, the variance of the divergence, right? So this means that the SGD divergence is going to be, variance is going to be much larger. Now, this math doesn't make a lot of sense to most people. It doesn't to me. So let's try to see it with pictures, okay? Let's say I'm trying to approximate this blue curve, and the red curve is the approximation that my model currently gives me with the current estimate W. Now, the height of the shaded region at any point represents the divergence, and the expected divergence is the shaded area. We want to find the W that minimizes this shaded area. Except that we can't, can you please mute yourselves, guys, whoever is talking? Right. Okay, so except we cannot compute this shaded area because we don't have the function everywhere. Instead, we approximate this shaded area as the sum of the average of the divergences at a small number of training instances. But the actual estimate that you get, so we are approximating the shaded area as the average of these lengths, right? But the actual estimate that you get will depend on the location of the training data, on the position of these points. So at these locations, for instance, the errors indicate that the red function must be pushed up at some points, and it must be pushed down at some points and pushed up over here. So with this particular set of training instances, this is the indication that you would get from the loss. On the other hand, if these were your training instance, then what is the assumption that you're going to end up with about the red function? What would you want to do? Anyone?
Shop everywhere?
You would want to push it up everywhere. Would that be correct?
Except for intersections.
Right. The point is, because the only training data you have are out here, you're going to end up trying to push the function up everywhere, right? Which is going to be the wrong thing to do in all of these locations. On the other hand, if my training data were like this, then you would be pushing down the function almost everywhere, right? So, so the solution to this, so basically different training data, different training sets will make you do different things to your function. So the quality of the update is going to be very dependent on the specific set of training samples that you have. Is this making sense to everyone?
Yes.
Yes, no. So how would you fix this?
Take a mini batch.
Mini
You
batch
need
is
more
going
data,
to
right?
you need more data. Taking a mini batch is going to reduce the amount of data, right? The only thing, the best thing you can do is to just have a much larger number of training samples. So when you have more training samples, then you're going to have less variation from training set to training set, and you're going to be more consistent across training sets in how you update your parameters. That making sense? Yes, no.
So we're still talking about using a single training sample to perform an update. It's just that the entire training set must have this variety.
And we are not speaking of the single training instance. I'm saying that this is what we do, right? What would happen if you had a single training sample? This is your batch update. And we are saying
Okay.
why having larger batches is better, right?
Right. Got it.
Right. Whereas if you had a single training sample, this is what you get. And depending on where the training sample falls, you'll end up doing different things. If the training sample fell here, you're going to think, oh, I'm just fine. There's no need to be performing any updates. If the training sample fell here, you're going to think, oh, I've got to push the function up. If it fell here, you're going to think, oh, I've got to push the entire function down. And so, which is why you're basically seeing this behavior over here, right? That when we perform batch updates, we have many more samples. And so the variance from run to run is relatively small. But with SGD, you have only one sample, so the variance is much higher, which is why you get this behavior. Does that make sense?
Yeah.
Guys? Okay, so how can you fix this? Let's come up with a compromise, right? So SGD uses the gradient from only one sample at a time, and so it's consequently a high variance estimator. But at the same time, it provides significantly quicker updates than a batch, because in a single pass through the training data, it updates the model many times as opposed to the single update that we get from batch updates. So we have this trade-off of frequency of update versus variance of estimate, right? So when you see this way, then you see that there's actually a medium. We can get an intermediate solution using mini batch updates. Instead of either updating the function at all training points simultaneously or updating it at only one point, we are going to sample a random subset from our training data, what we call our mini batch, and update the model there. So we might randomly choose these 3 points, for instance, and update the model at these 3 locations, which will push the function up in the first place and down in these 2 locations. Then you choose a second mini batch around a different set of points and adjust the function at those points, giving us yet another update, and so on. And if we continue to repeat this process, drawing random subsets of training instances from our training set and updating with those the model with those points at each time, we will eventually cover the entire training set. And as in SGD, we're not going to make very big adjustments, but keep the updates small within each mini batch. But eventually, we would still have updated the model everywhere, and in a single pass through the entire training data, in which we will fit many mini batches, you would have had made multiple updates. And so hopefully this gives you a better effect than with either simple SGD or batch training. And again, as before, for this to work, the process requires randomness. We can make multiple passes through the training data, but in each pass, the manner in which we choose the subsets must differ. So here is the pseudocode for mini batch update. This is essentially the same as SGD. We make multiple passes within the training data. This is our epochs. Within each epoch, we're going to be working on batches of data within each time. But within each epoch, we also first shuffle the data to make sure that these batches are randomized. And so we're going to be operating on batches of data, and you're also going to be reducing the learning rate with iterations for the same reason that you did so with simple SGD. Now, in each iteration, the loss minimized by the mini batch update is the average divergence. This for the mini batch, the loss is not the divergence for a single instance. It's not the divergence over the entire training set. It is the average divergence over just that mini batch, right? So what is the expected value of this mini batch loss? Can anyone tell me? What is it going to be? Anyone?
It should ideally be the same as before, right?
It's exactly the same, right? Because if I take the expectation, you get 1 over b outside, then I'm going to get a summation of the expectation of the divergence, b of these. So 1 over b times the expectation of the divergence. It's exactly the same as before. The b's cancel. The mini batch loss is an unbiased estimate of the expected loss. What about the variance? Anyone?
1 upon b.
It's going to be 1 over b, right? So this is 1 over b, the variance of the individual divergence. And so now let's compare this, right? How does this work? Let me say, if I can pull up my slideboard, right? So let's say this is my mini batch size, and this is my full batch size, n, right? And this is, come on, okay. And this is my variance, right? So when the mini batch size is 1, I'm going to get a scaling factor of 1, right? When the mini batch size is n, this is going to be 1 over n. N can be very large, so this can go down to almost 0. But then observe how, because this variance falls off as 1 over b, the variance is going to fall very rapidly. By the time you get to about a batch size of 100, the variance factor is already 0.01. Even at a batch size of about 30, the variance factor is going to be 0.03. So you can see that when you begin working in mini batches, this variance is going to fall very, very rapidly and is going to begin approaching the variance over the entire training. Right? This is going to begin approaching the variance over. Someone shut your mic, right? Right. Variance over the entire training set very quickly, right? And so the mini batch update gives you this advantage that you get almost as low variance as you do with the full batch, but you still manage to get, if you have n training samples, n over b updates in a single epoch, a single pass through the data. And so that actually gives you this kind of behavior. Returning to our k-means example, if I include the curves for mini batch descent, what we see is that this is the mini batch descent. This converges as fast as SGD, but it converges to more or less the same error as batch descent. So, questions? Questions, anyone? I guess not. So you see the difference between mini batches, SGD, which are updates after each instance, and batch descent. Batch descent is minimizing the loss we actually want to. It has the lowest variance of all. But then mini batch descent gives you many more, substochastic gradient descent gives you many more updates per pass through the data, but it's very noisy. Mini batch descent gives you multiple updates, but still manages to retain low enough variance. So this mini batch descent tends to be a method of choice. And specifically, the parameter that we end up having to worry about is the mini batch size. The larger the mini batch size is, the lower the variance is going to be. At the same time, having too large a mini batch means that your data, you're going to be processing more data for each update. You're also going to run into things like memory issues and so on. But nevertheless, this is clearly the method of choice. Now, one of the issues is how we actually measure convergence. It's generally defined in terms of the overall training loss in the entire training data. That's what these figures actually show. In these examples, after each update, they ran the entire data through the model just to compute the loss. But in the real world, you'd never do that. It would be very stupid to update your model using a mini batch and then process the entire data just to compute the loss. You would never do that. So you have to estimate the loss on the entire training data from what you compute from the mini batch. So typically we estimate it as the average divergence or classification error on some held out set, or we maintain a running average of the sample or mini batch losses over the past several samples, and these are the numbers we will report. Now, in practice, so training is usually performed using mini batches, but the mini batch size is a hyperparameter to be optimized. We want them to be large enough to have low variance, and yet small enough to get the maximum number of updates at each epoch. Also, the convergence depends on the learning rate we used, and the learning rate must satisfy the criteria we saw before for SGD. So the learning rate schedule, the values it will take and how they change with iterations must be carefully chosen. And the simplest popular approach is to fix the learning rate until the error plateaus, and then reduce the learning rate by some fixed factor, say 10, and then keep it fixed till the error plateaus, and keep doing this and observe that this learning rate also satisfies the property that it's converging and yet remains not absolutely summable. So Anurag, can you release the next poll? Ten seconds, guys. All right, let's stop this. So Minibatch descent is the same as SGD, but the batch size is 1. So the second option is wrong, but the rest are right. It is an online version of batch updates. The variance of the mini batch decreases with batch size and increasing batch size, and mini batch gradient approaches batch updates in variance, but SGD in efficiency when we use large batches and vector processing. So here's the story so far. SGD presents training instances one at a time to be more effective than full batch training, provided they are presented in random order. For SGD to converge, the learning rate must shrink sufficiently rapidly with iterations. Otherwise, the learning will continuously chase the latest sample. SGD estimates have higher variance than batch estimates, and mini batch updates operate on batches of instances at a time. The estimates have lower variance than SGD. Convergence rate is theoretically worse than SGD, but in practice, it's much better. And we compensate by being able to use parallel processing over the batches. So there are a few more, there's some more information on the slides. Please look it up. Anyway, so our next topic for the day, I have 15 minutes, I may run over by a few minutes, is trend algorithms. We've already seen them a bit. So we'll be revisiting them. By trend algorithms, we mean algorithms that use prior trends and the updates to estimate the next update, like momentum methods. Now, in the batch update case, trend algorithms only serve to speed up convergence. In SGD and mini batch, they serve an additional purpose. In these incremental methods, the loss function itself varies from iteration to iteration. So this causes a variation in the updates, and it causes your gradients to oscillate around. And so the trend methods smooth out the effects of the variance in the loss function across iterations, and so the trend methods end up becoming somewhat critical for optimization. Now recall the first trend method we tried, momentum. In the momentum method, we maintained a running average of the past updates and the current gradient. So given by this formula over here, we saw this in the last class. So the kth correction, delta WK, is some beta times the k minus 1 correction minus this eta times the gradient. So this is the gradient update, and this is the component from the previous update, which gives us our running estimate. So pictorially, if this first red arrow here were an initial update delta W that lands us at this point, then we compute the gradient-based correction, the sum of the gradient-based correction and a scaled version of the previous estimate to get the final correction at this point, the previous correction to get the final correction at this point. That would bring us here. Then again, you compute the gradient update from this point, but you add to that a scaled version of the last update. And so this is your final update, and that would take us here. And we keep repeating this process. When we perform SGD or mini batch updates too, we're going to use momentum in exactly the same way, where the kth correction is computed using the same momentum formula over here with one minor change. The loss, whose gradient we are computing in this update, will be computed from the kth mini batch, or if you're performing SGD, then it's going to be from the kth sample drawn during training. So SGD and mini batch updates, they tend to have higher variance, and the smoothing effect of momentum has greater benefit. It can lead to smoother and faster convergence. So I have the pseudocode, let me skip that. Now, Nesterov's method, we will recall, is a variation on the basic momentum method where we reverse the order in which we add the gradient step and the previous update. So here in any iteration, to compute the current step, we first extend the previous step and then compute the gradient correction at that point to get the final update. So this technique also applies directly to incremental updates. And the accelerated gradient also smooths out variance in the gradients. So for Nesterov's accelerated gradient, we're going to use the same formula as before, as regular Nesterov's method, except to get the kth correction, delta wk, the gradient term that you're going to use within the update rule, that is going to be the loss computed at the current position, the gradient of the loss computed at the current position on the current SGD instance or Minibatch. So the only difference between what happens in the batch technique and SGD or Minibatch when we use Nesterov's method is the definition of this loss, which is constant across iterations for batch updates, but itself changes from update to update when you're using SGD or Minibatch. So momentum and Nesterov's method improve convergence by normalizing the mean of the derivatives. So they're based on the idea that when you have derivatives which oscillate around like so, then if you take the average of all of these guys, you're going to get a derivative that's much more representative of how you want to go along the parameter space. So in directions where all the derivatives are consistent, this will give you a nice long derivative. In directions where the derivatives keep changing direction, it's going to average these things out. This idea is good, but it ignores one important feature: the actual degree of variation when things oscillate. So for example, if I have, suppose I have two different error surfaces. In one case, I get these derivatives along the y direction. In the other case, I get this. In both cases, the average would be the same. But yet, which of these two seems noisier to you? Anyone? Which one seems noisier? The first one, right? Obvious. Because this is bouncing around a whole lot more. Here the derivative, I'm just showing you the y component. And so the y component is swinging wildly over here, and this y component is not swinging very much over here, right? So when you have this, you basically want to trust the y component much less in this case than in this case. Because even though it's swinging around, it's sort of consistent. Here it's swinging wildly. And this issue is something that the standard momentum methods ignore. And so more advanced methods like RMSProp, AdaGrad, AdaDelta, and Adam actually consider the degree of variation, not just the mean, but by how much it oscillates around. They consider not just the first moment, but also the second moment. So let's take a look at this behavior again. Consider the example to the left. This is a typical plot for update steps. You can get such behavior even when you're using momentum or Nesterov, particularly for SGD or Minibatch because of the variance. What you observe is the estimate moves a lot. The total movement is quite a bit. But then if you consider two consecutive steps, the actual distance in which the update has moved is this much plus this much, but the net is only this much, right? If you take it over all of the steps, it's moved around so much, but the net is only this much. And so if you look at the total movement in each of the X and the Y components, you will see that in the X component, it's consistently moving 1, 1, 2, 1, 1.5. The actual, extra movement that's happening is happening because of the Y component where it keeps bouncing around. So our idea is to try to dampen the movement in directions where it's moving a lot, but without much net movement, and sort of maintain or enhance the movement in directions where it keeps consistently moving in the same direction. And so we'll modify our usual update rule. At any point, we're going to consider the updates in the recent past and scale the updates for each component in inverse proportion to the total motion in that direction. So if you take this guy over here, here the total motion in the x direction is this much, this much, this much, and this much. So it's consistent. So the net movement and the total movement are very comparable. Whereas if you look at the y direction, it's this much, this much, this much, this much. But the net direction, total movement in y is very small, right? So we're going to look at the total movement to the total variation, and the total variation we're going to capture using the second moment, not the average, but the second moment, because the average is not going to distinguish between this and this, as we saw, right? So instead of taking the average, we are going to try to look at the root mean squared value, which doesn't cancel things out. The positives and the negatives don't cancel out. The problem with the average is that the average lets the positive movement and the negative movement cancel out. The root mean squared value is just going to effectively take the magnitudes of these guys, and so they don't cancel out. And so in directions where the RMS value is very high, you're going to try to reduce the step size. Where the ratio where it's low, you're going to try to increase it. So the first technique, I'm going to run about 4 minutes over, guys, just bear with me, right? Which embodies this is RMSProp. This is very popular. It's a simple technique that uses second moment based scaling. To explain it, I'm going to use the following notation. This is simply the derivative of the divergence with respect to W. When I write d squared dou squared W, this is not the second derivative, it's the square of the derivative. And when I want the mean squared derivative, I'm going to just write it as an expectation. This is just simplified notation, right? And so RMSProp is a variant on the basic Minibatch SGD algorithm. What we do is to maintain a running average of the mean squared value of the derivatives for each parameter. And by maintaining the mean squared value, it just accounts for the total movement without letting the positive and negative movements cancel out. So this is, in some ways more reasonable, right? Think about it. If you think of the average error of a stationary clock, it's 0 because the positive and negative errors cancel out. But if you take the RMS error, it's going to tell you the RMS error of a stationary clock is very large. So the Momentum and Nesterov take the average error and sort of behave in a manner which tells you that on average, a stationary clock is fine. But something that considers the second moment is going to tell you it's very off. And now the actual update that we will use is going to start off with some initial learning rate, but then it's going to scale the learning rate down by the root mean squared value of the movement in that direction. This epsilon over here is just intended to make sure that you don't get a divide by 0. So this is just like SGD, that's just like gradient descent, except that the learning rate is always scaled down by the root mean squared value of the derivative for that component. So now observe how this is very similar to RProp. If you have a constant slope, then when you have if your loss function has a constant slope, then the root mean squared value is going to be the same as the magnitude of the actual value itself. And so when you have a constant slope, this term is going to be magnitude of the slope. And so the update is simply going to be WK plus 1 equals WK minus eta times WK plus 1 equals WK minus eta times the derivative divided by the magnitude of the derivative, which cancels these out. So this is simply going to give you WK minus eta times the sine of the derivative, right? So this looks a lot like RProp. And in fact, RMSProp was originally named RMSProp because it was viewed as an extension of RProp. Now, RMSProp is nice, but it's still somewhat, it's missing something. RMSProp is only considering the second moment of the movement. Momentum only considered the, and Nesterov only considered the first moment of the derivatives, right? Why don't we combine both? And when we combine both, we end up with Adam. So Adam now considers both the variation and the average of the gradients to compute smooth estimates. It considers both the first and the second moments in the update rule. So to do so, now you maintain two running averages. First, it maintains a running average of the mean of the derivative for each parameter. But then it also maintains a running average of the mean squared value, just like RMSProp for each parameter. And then the update rule over here is using the running average of the derivative rather than just the instantaneous derivative that RProp was using. So RProp was just using the instantaneous derivative. RMSProp is the same as RProp, except it uses this running average. Now there's some magical thing going on over here in between. And what is this odd magical thing? That's simply a way of making sure that things don't blow up. So typically, when you maintain these running averages, these gamma and delta are going to be very close to 1. And the initial value when you're doing these running averages is going to be 0. So in the initial estimates, what will happen is that because gamma and delta are close to 1, these terms will go to 0. And so your running averages for the mean and the mean squared value are going to remain close to 0 for several estimates, making your updates unstable. So what we do is, rather than using these raw mean and mean squared values, we divide them by 1 minus delta raised to k. When k is 0, or when k is close to 0, this becomes a small number, and so it scales up these guys. But then as the iterations increase, this term is going to become 0, and so this denominator simply vanishes. So just make sure that in the initial iterations, the behavior is not too slow, but then with the iterations, the denominator term becomes large enough to become a non-factor. The key point, of course, is to remember this, that the update is just like your standard SGD, except here you use the running average of the derivative, and you scale the learning rate down by the RMS value of the derivative. So there are other variants on the same theme, like add a grad, add a delta, add a max. They're all essentially some variants on the simple concepts that we just saw right now. All of these have exactly the same feature, because the learning rate is sort of adjusting itself with this RMS value. So you don't need to plan a learning rate schedule. These things the learning rate will automatically shrink and get you to the optimum. You do have other hyperparameters to set anyway. So like the initial value for eta, this gamma and this delta, and here are some typical values for RMSProp and Adam, but these are terms that you can play around with. So there was supposed to be a quiz here. I'll skip that. What I have here is a couple of visualizations that Alec Radford came up with on his website. So I'm going to try to show this. Those of you who want to leave can leave now, but these are pretty pictures. If I can pull them up, and if I can figure out how to pull them up. Let me see. Windows is such a pain. Somewhere here is a PowerPoint, so I can't see this. Apparently, I can't see the PowerPoint. Right? So let me skip that. But I'll put these 3 PowerPoint slides up on Piazza, and you can see how the various techniques behave. And the behavior is can be explained based on the intuitions that we just developed. So anyway, so the story so far: gradient descent can be sped up by incremental updates. Convergence is guaranteed under most conditions. Learning rates must shrink with time for convergence, and SGD updates the parameters after each observation and can be faster than batch learning. Minibatch updates update after batches. Convergence can be improved using smooth updates like RMSProp and more advanced techniques. So we'll stop right here. I'll make one more vain attempt at trying to pull up the slides. So you can see how this he's comparing different optimization techniques on this function called Beal's function. The optimum values out here, and you can see SGD generally, SGD, which is this red curve over here, generally takes its time getting there. And all of the other techniques, which are considering these first and second moments, generally tend to get there very fast. Here's the interesting thing: things that sort of normalize using the RMS value, like ADA-grad, ADA-delta, and RMSProp, they get to the optimum somewhat consistently, but momentum and nest troughs, which tend to wander off, often get to the solution faster than ADAM and ADA-grad. Here's another example. This is the long valley, and you can see that in this case, ADA-delta took off very early, and SGD just sort of got stuck in the middle right here and never moved, because that's where the derivative was 0. And Nesterov and Adam sort of swung around for a bit, but then Nesterov and momentum. But then when they came down really fast, and they beat RMSProp and some of the other techniques. And if you sort of plotted it all the way to the end, I think you'd find that Nesterov gets there fastest. Here's another one. This has a solution. The optimum is down this line, and once again you can see that the ADA techniques, which normalize the step size by the RMS value, they move down somewhat consistently. SGD gets stuck. Momentum and Nestrovs, they wander off, but when they find the path, they really sort of zoom out, right? So you're going to get typical behavior in. You can actually predict which of these techniques is most likely to get to the solution faster if you know the topology of the loss function at any point. Unfortunately, we don't, so you end up having to take a guess. So I'll stop over here, and I'll stop my recording. If